later. Yeah, as we speak, people are beginning to log in. So I think let me give a brief introduction about the QSR seminar webinar series and the user interface here, and the introduction of Dr. Yu Ding before we begin. So everyone is muted by default. If you usually to make things easier, we will talk. We will do Q&A sections after the presentation of Dr. Yu Ding. But if you really have some really burning questions, you have to ask now. You can raise your hand, and we can try to fit in the questions in the presentation. Okay, so this webinar is the first webinar, one of the most important webinar in this new QSR webinar series. So our first presenter is Professor Yu Ding from Texas A&M University, and the topic is wind turbine reliability and performance assessment and the data science relevance. So without further ado, I will move to Professor Yu Ding.
Okay, thank you very much, Lincoln. I hope everyone can hear me. If you couldn't, you probably should raise hand so Lincoln can help you to get connected. And so good morning, everyone, or good afternoon, depends on which time zone you are. And I certainly feel the pressure because I'm the first QSR webinar speaker, and I hope I don't really ruin the webinar series. So today, the topic we're going to discuss is related to the wind energy research I've been doing in the past about more than 10 years. I gave the same talk back in summertime at Beijing's Quality Reliability Workshop hosted by Chinese Academy. So if you happen to be in that workshop, listen to this talk already, and this talk is virtually the same as that talk, so you don't have to be here anymore. And then, but if you haven't, of course, you are welcome to stay. And if we have some time, we can engage some question and answer afterwards. So we've been doing wind energy research for 10 plus years. And the wind energy growth in the US also has changed quite dramatically in that time. And these slides basically give you a sense of the wind energy installment as well as the electricity that produced in the United States. So the figure on these bars is on the installment. Of course, not all the installment really convert to the useful electricity, but still the electricity produced by wind energy, when we started the research, is about 0.5%. and around that number. And right now it's almost become 6.5%, 6.3 to be precise last year. So that's the order of magnitude increase. The installment actually increased even a little bit bigger. So the wind energy has grown from very tiny player to a quite sizable player. It's one of the front runners in the renewable energy source. So the solar energy compared to the wind energy right now, this year, is almost like the wind energy back to 20 years ago, about 0.5% electricity produced by the solar right now. So about 10 years ago, around 2008, the US Department of Energy published the white paper and then revised that white paper subsequently. Initially, the white paper's name is called 20% wind by 2030. Okay, so the idea is the DOE contemplate the scenarios. The wind energy will contribute electricity produced and used in the nation 10% by 2020, 20% by 2030, and 35% by 2050. And if you think about that goal set by the DOE, it's not really very easy to accomplish it. If you look at the history, increase from 0.5% to 6.5% takes more than 10 years. Okay, so every year the increase in percentage number is less than 1%, and we only have about 2 more years left until 2020. So if you want to achieve 10% by 2020 from 2017, and you have to increase more than 1% every year. And that may not necessarily be very easy to accomplish. Also, if you think from another angle, the 35% by 2050, actually that's quite a big deal. If when they produce the electricity at the level of 35%, and you can imagine the solar probably will provide energy or electricity at 20%. So altogether, these two sources will give you more than 50% of the electricity used in the nation. If the proportion of the hydropower and nuclear doesn't really dramatically decrease, as nowadays they stand at 20%, 16% and 20% respectively. So if you add all these kind of carbon emission-free energy sources, they all add together will give you 90%, 91%. Okay, and then you only have oil and gas to give you electricity less than 10%. Okay, so that is a quite ambitious goal to contemplate by the Department of Energy, and whether or not we can really accomplish that, and it's still way to see. And one of the challenges to wind energy growth is still the marketability and market competitiveness. Because for a long time, wind energy cannot really compete in the market by itself. It actually being subsidized by a mechanism called Federal Production Tax Credit, and in short, PTC. Okay. Now, if you want to just roughly consider, what kind of energy really make money in the marketplace, you can think of this magic number about 5% per kilowatts. That's the wholesale electricity price. And of course, when we use the electricity at our house, we have to buy the electricity at a much higher price, like 10 cents or 11 cents. And that's a retail price. So the wholesale price, 5 cents, if you can produce the electricity around 5% or below 5%, you're almost guaranteed to make money. Okay, if you do that at 7.5%, and you are not competitive. In between, sometimes depends on time and location. Okay, so for the onshore wind, the cost of energy in the past number of years, they were able to kind of reduce that between the 6 cents and 7 cents per kilowatts. Okay, and the offshore wind is still much more expensive. It's out of the range of being even closely to be competitive. But we have plenty of onshore wind farms. Okay, suppose we use a 6.5 cents per kilowatts as the average cost of energy. And back in 2016, the PTC stands at 2.3 cents per kilowatts. If you factor in that federal subsidy, of course, they give a huge boost of the wind energy's marketability. With the 2.3 cents and the cost of energy on average is below 5 cents per kilowatts. Okay, and the federal PTC works in a way, as long as you start the wind farm in 2016, you're going to enjoy that benefit for next 10 years until 2026. Okay, as long as you start constructing the wind farm in 2016, that benefit will stay with you for 10 years. But the federal PTC is phasing out, and it's kind of reducing by 20% margin every year since 2016. So last year is 1.9 cents, 2018 right now is 1.4 cents, and if it goes on schedule, by 2020, the PTC will be gone. Okay, of course, the political environment could be different, and the Congress could pass a different law to kind of bring back the PTC. But the bottom line is still, and without the federal tax credit, and the wind cannot entirely compete with the lower cost energy sources in and by itself. Okay, so reduce the cost, improve the efficiency, improve the reliability is still very important objective for wind energy. Okay, so how much the cost related to the reliability aspect, and oftentimes people use the O&M cost to kind of characterize that. And there's a different kind of estimate. And back to about 15 years ago, the estimate of O&M is very much kind of optimistic, right? If you look at the DOE 2004 estimate, it's only about 7-8% of the total cost. Okay, but this kind of estimate being revised always kind of going up. Okay, the recent estimate by IEEE or published by IEEE Spectrum and put the O&M cost almost at the 32% of the total cost. Okay, so Dr. Felker, the former director of NWTC, National Wind Technology Center, gave a presentation around that time. And one of the slides has the title, the critical element of this 20%, the 20% wind by 2030 scenario. And he lists the 4 elements over there. One critical element is reduce O&M cost by 35% from that year's level, right? If you think about that year's level, it's about the 3 cents per kilowatts is the O&M cost. 35% of that 3 cents is about 1 cent. Okay, so if you go back to this previous slide here, if we have 6.5 cents per kilowatts, you get 1 cent reduction from the cost, and obviously you get very much an improvement on the competitiveness of the wind energy. Okay, so that is highlighted of the O&M part. The cost reduction is one of the major challenge, and also the area need a lot of research and development. Okay, so why wind energy or wind turbine is unreliable? And this factor is really kind of very deeply rooted in the operation of wind turbine. As you can easily imagine, the wind turbine, the wind energy is called a variable renewable source. So the driving force for wind turbine is changing all the time. The wind is not something we can control. The wind blowing over the wind turbine. So the non-stationary wind force, in fact, subjects a turbine's drivetrain to a constant fatigue load. An analogy we often use is really saying, if you have a car, if you drive the car almost on the cruise speed, constantly, or most of the time on the highway, and you probably don't really kind of, you have the car at a longer service life. But on the other hand, if you rarely get on the highway, you drive the car in a very busy city with a lot of traffic lights, and so you stop and start and very frequently, and now you're going to have a shorter service life of your car. Okay, and this is the car driving in the city life is really the type of analogy for the wind turbine, because the wind is not controllable, and sometimes you have strong wind, sometimes you don't have strong wind, and the very persistent wind, very strong driving the wind turbine rotate, and doesn't really always kind of last very long. So you have the turbine kind of up and down in a very frequent kind of changeover. Okay, so the non-steady load for the wind turbine force is one of the major driving force caused the unreliability of wind turbine. On the other hand, given the size of the wind turbines, and you probably never see actually commercial wind turbines get a cover, right? They kind of operate in the open environment. So the wind gust, icing, lightning, all these kind of damaging environmental conditions, and will contribute to the additional unreliability aspect of the wind turbine. Okay, so when we talk about reliability, we often use this kind of bathtub curve, right? Here I flip the bathtub curve. Typically, the bathtub curve is kind of going down here and flat and then going up. So the vertical axis here is the reliability or the so-called mortality of the parts. And here when I flip this part, so this vertical axis is the reliability, or sometimes we call it operational efficiency, with kind of break-in period, or sometimes people call burn-in period. And you can see a kind of increase of the operational efficiency. But for the longer period, you're going to expect the stable operation condition until it getting close to the end of the service life, you have the accelerated decrease of operation efficiency or reliability. What we suspect for the wind turbine is not really a bathtub like this. It's something more like this. Now, there's not enough study yet to kind of confirm exactly this kind of curve. There's some initial study does give knowledge about something for this to happen, right? You still have this kind of initial period of the break-in, and now you have much shorter period of the stable operation. And now you have this decline, noticeable decline before you reach the end of the life, service life, okay? And so this bathtub curve bears some kind of relevance, and we will come back to that point a little bit later, okay? The challenge or the difficulty in the wind turbine O&M, operations and maintenance, and I like to use 3 keywords to summarize that. One is size, another is weather, another is distance, right? The size of the turbine is huge. And sometimes we don't really have that feeling because we typically see a turbine from distance. But if you take this picture from an online source and compare this wind turbine with other kind of structures, right? This is a new GE turbine, and the tip height is 853 feet. So it's almost close to 300 meters. So that's very high, right? The hub height here, the middle part here, and could be more than 100 meters high. And if you compare with like Eiffel Tower, it's slightly higher than that one. People said, you have this kind of large structure, why this kind of structure can stand over there over 100 years, and what's the problem with wind turbine? But you don't really have a kind of moving parts on top of this kind of tower, right? Or the Empire State Building. But you have this very large load turbine blade is kind of constantly rotating on the nacelle or on the rotor. So that kind of exercise a very strong force. And each of the blade is also very heavy, right? Even with about 50 feet blade, it weighs about 16 tons each. So this large turbine is weight even more. So 3 blades together is almost like 50 tons. So that kind of size over there, it also caused other kind of difficulty. For example, the turbine blade is very hard for you to have a warehouse nearby the wind farm to have all the spare parts stored over there. Gearbox is huge, and also it's very expensive. So whenever you have a problem, you probably will have to endure a long lead time because you don't really have the spare parts to replace. You have to order that, and the ordering, delivering takes a lot of time. And in order to kind of fix the problem, you have the heavy duty equipment has to be used, okay? And each time you call the heavy duty equipment or the crew to be dispatched, and that the sunk cost is actually considerable. And because of the wind turbine, the size, the kind of stand outside in the open air environment, and the weather also caused the problem for the O&M activity. There's a lot of disruptions. They could cause a problem for you to access the site, and even your O&M activities ongoing, and with some kind of forecast of adversary weather condition, you probably have to stop, and now you have to kind of withdraw to a safer place, right? Both of the strong wind and lightning and the storm, the rainstorm, could cause a problem to the ongoing O&M activity. The distance is also a problem, right? You don't really have your wind turbine or wind farm to your next door, and on the busy cities, most of the time it's really kind of the maintenance center or the data processing center where it's located. And so you have to drive, for example, from Dallas to its west to its wind farm, almost it's 200 some miles away from west of Dallas, and or from other major cities. And by doing that, it's very expensive. So some of the decisions, even you see certain kind of signal, give you an inkling there might be a problem, you always hesitate whether or not you should kind of undertake that kind of expensive action. And the uncertainty in the action option together with the expensiveness of the consequence. And either way is expensive, right? You dispatch the crew, it's not economical. And without doing that, should anything happen, okay, it's also a difficult consequence to face. So for assess the reliability aspect, people often do the load assessment sometimes fatigue load assessment, and sometimes extreme load assessment. Here, the load we are talking about is mechanical load, okay, measured in terms of flap-wise and edge-wise bending moment. So we have a schematic diagram here and indicate there are certain kind of critical spots on the structure of wind turbine, like the root of the blade and the shaft and the tower positions. You have different kind of bending moment, and those bending moment has a very strong relevance about the service life of the major structure. And we use this Z variable to denote the extreme load experience. The fatigue load is the same thing, but the extreme load is a little bit easier to understand here. Now, the extreme load can be defined through an extreme quantile value and via this distribution, right? If you have the distribution of the Z, and then people need to define or design this withhold capability, how much the material and the manufacturer of wind turbine can resist this level of the extreme load, such that during the service life of 50 years, the probability of this kind of extreme event happening is very, very low, okay? And the IEC, this international standard body, does publish the guidelines and what kind of low probability you need to use in order to calculate the design parameter, okay? The design parameter is going to be materialized or accomplished by selecting certain material and also the manufacturing process to make sure they hold together, okay? We want this kind of event happen in a very small probability, and therefore the turbine is not going to be damaged in that kind of weather condition. If this condition is true, if the Z is the extreme load on the turbine structure greater than your design threshold, and then you're going to face certain kind of structural damage, a rupture of the turbine blade, and sometimes even the collapse of the tower. On the other hand, in terms of the performance assessment part, and people like to use this power curve. The power curve is a functional relationship connected the wind speed and to the power production. And here we use the Y to indicate the power output. You know, previously we used the Z to indicate the load assessment. So the power curve often follow this kind of shape. A certain kind of wind speed, for example, 3 meters per second, and the turbine start kind of producing electricity with the turbine, the wind blows stronger. And then you have this turbine reach to a certain kind of point, and you followed by a certain kind of control mechanism, and then reach this kind of threshold, the saturating level. We call the rated power, and the corresponding wind speed is called the rated speed. And then if the wind belongs even stronger to the level of, we call it cut-hour wind speed, and this wind speed is too strong, for example, 25 meters per second, and then there's a mechanical brake can stop the wind turbine at that point. So we have the reliability aspect, we have also the performance assessment, and the system level performance assessment is typically achieved by using this the power curve. Okay, so a data science formulation in the wind energy, and by using the power output Y, considering the variability or stochastic nature of the wind input, and can be expressed by this probability expression, okay? And here, the P of X certainly is the probability related to the wind field. It's not necessarily only the wind speed, but most likely the wind speed is the most volatile variable among all the environmental conditions. And then you have this conditional probability. It's really given this kind of wind and input condition, how much power you're going to produce in the probabilistic sense. And this is directly related to the turbine performance, okay? And then if you integrate out of the X, and you have the probability of Y, which is the probabilistic, the wind power production, okay? If we substitute Z, the extreme load condition on the wind turbine into this equation, almost without changing anything, this equation still holds, right? And here is the response is mechanical load Z, and still the P of X is the stochastic nature of the wind field, and then the P conditional probability or conditional density, the PZ condition on X, and this provided the understanding of the turbine's endurance. And if you integrate out, you have the X and you have the unconditional load on the turbine, and this is the probability of Z. So Lincoln, I think there's one person raised their hand. Lincoln, can you hear me?
Yes, I'm typing the question to one of the
Okay.
Yeah.
Okay, so I can continue.
Yeah, please.
Okay. So we have both of this data science formulation, and people said how they are related to each other. And here, I'm sorry. Here we use the conditional density Py conditional X for performance, Pz conditional X for reliability. But when we use these equations here, we sort of assume the wind turbine is operating, okay? But the wind turbine is not reliable all the time. So when it's not reliable, it's kind of in the downtime, and certainly this equation shouldn't be called into service. And for factoring that reliability connection, we could possibly put the indicator function here and related to reliability. If the turbine is reliable is operating, and this indicate condition give back a 1, and now you can use the rest of the equation to evaluate the probability power production aspect of Y, and by integrating out the variability of X. But this reliability part certainly is related to this the load assessment in the large aspect. And this formulation also can allude to a control problem, because here we only have an observable variable X. The X is not entirely controllable, not by us, okay, not by human, okay. But on the other hand, there are other kind of control mechanism on wind turbine generator, like yaw control or pitch control. And if you consider those kind of controllable input, you could possibly trade off between the power production, or at least the near-term power production, and the longer-term, the reliability, endurance of the turbine, or the load assessment on the turbine. So you can sacrifice to some extent of the short-term power production, and then you can, for the benefit of the longer-term reliability. And this is like, the human beings, we often take vacation to be away from work, and for the purpose, we can work longer and have longevity and have more production the lifetime. Lincoln,
Professor Eugene, there's a question asking if you can go over slides 11 and 12 quickly about the data science formulation.
11 and 12, okay.
Yes.
So ask me to do that one more time.
Yes, there's a question about the formulation here.
So here, this is the conditional probability, right? This is unconditional probability. If you try to understand the output of the power, which is probabilistic behavior, and then, of course, you can collect the data of Y to directly evaluate this part. But by directly evaluating that part, you sort of kind of have two confound factor in it, right? How the turbine itself perform, and then the variable input from the wind. So in order to understand the turbine's performance under a given wind or environmental condition, it's quite important to the wind industry to understand this conditional density. Okay, and obviously, if you have the conditional density, and you can always integrate out the X variable to get the output. Okay, so to understand here, suppose you want to predict the wind power in the future, right? So what you want to do is, based on the understanding of the variability of the wind, you can predict the wind speed first. And then you have this kind of relationship said, given that wind speed, how much power you expect that wind turbine will produce. And if you get these two information, get the power prediction. And together, because this is all in the probability sense, it also gives you the uncertainty quantification very naturally. Okay. For the load, it's the same thing. For example, people do the load assessment because this is related to the design parameter, but they don't want to do that for every commercial turbine in every wind farm. Okay, they can collect the wind farm wind condition from historical data collection process, but before they kind of put the wind turbine on a new farm, so they don't really have this information, or they don't even have directly the information from that wind turbine. So what they can do, they can based on the test turbine data collected probably at a different place, but with enough the X even in the old site or test site to give you this conditional response of the load on that particular turbine model. Okay, so you don't have to run this one in the new site. You only need to collect the wind data in the new site and plug in this both of the quantities here. You can do assessments that in the 50-year service for the new wind farm site, and what is my expectation? What is my expected the probability density distribution for this load? And therefore, I can say with this kind of design threshold, the L sub t we used previously, whether or not this is enough for me to kind of avoid a catastrophic event to happen. Okay, does that help?
Yeah, I believe that answered the question.
Okay, so let me go a little bit further from this slides. So one of the immediate questions, of course, given the importance of the performance assessment as well as the load assessment, and what do people do in industry, right? They must have been doing something, right? The type of method you use actually is pretty simple. It's called the binning method. Okay, the idea is very easy to follow. Suppose we have the response is a power output Y. So you have this kind of data. This is real data collected for one particular wind farm, a wind turbine. Okay, this is the wind speed. This is power output. Okay, and then in order to get the power curve, industry simply kind of partition the wind speed into small bins. For example, 0.5 meters per second. Okay, for each bin, here is the amplified, magnified version. So you can see this is the bin number 1. It's all this kind of red dot, the green dots is in that bin, and you simply just average all these data points here. This is power data, right? And use this average to represent all the data points in that bin. Okay, and you do that for the second one, the neighbor bin, and with all these blue dots, and you do the average. Okay, now when the response is you can also, for example, here you can also feed for example, Gaussian distribution, if you will, or you want to feed a skewed distribution like Weibull distribution. You can get a little bit kind of distribution understanding from that bin as well. For when the response is a mechanical load Z, and obviously it's not very easy for you to just feed one simple average, because the extreme load really kind of related to the tail distribution. You want to calculate the tail probability. So here people use the GEV, is a generalized extreme value distribution. Weibull distribution is one of them. Gumbel distribution is another one popularly used. So on the other hand, the GEV distribution has 3 parameters: the location parameter, scale parameter, and the shape parameter. It's not really easy for you to use the GEV distribution has all the parameters as a function of something else. Okay, it's much easier for you to use them if you fix all the 3 parameters. So in order to fix the parameter, you need to make the distribution somewhat kind of homogeneous or stationary. Okay, therefore, the practitioner decides simply just to kind of cut a bin. And here the bin size usually is a little bit bigger, for example, 2 meters per second, but still it's kind of a small interval. They collect all the data here. They assume all the data coming from a constant parameter GEV distribution, and they use the data to estimate mu1, sigma1, psi1. Okay, and then they do for the next bin, and they estimate the constant parameters over there. And then eventually they use this integration to kind of stitch all this kind of bin-wise GEV distribution together. Okay. Now the binning method, however simple it looks, it actually has its own merit. Okay, number one is very simple, and that is actually a good thing in industry, in practice, because people usually don't like to use very complicated procedures, and the manipulation of the data they don't fully understand. On the other hand, the binning method is also very adaptive. It doesn't really kind of make too much assumption. They make some assumption for sure, right? They assume it's kind of either a constant or it's a kind of a constant parameter distribution for each bin. Okay, and that's pretty much the assumption they use. Okay, that is the reason they've been used as a simple procedure like to handle this kind of non-linear, non-stationary, inhomogeneous the estimation problem. But they don't really make assumptions about what kind of function they form. So by and large, and by the nature of the binning method is a non-parametric method. So it's pretty adaptive to all different kind of data from different kind of turbine model with different kind of control mechanism we use. Okay, so even there's a fair amount of physical understanding for example, the power production aspect. Okay, the understanding for the load is a little bit kind of it's not as well understood as the power production. But even as the power production is pretty well understood, the function form itself is not necessarily easy to use. People write this wind production law in this kind of form. This equation looks pretty simple, right? The power production equal to this constant 1/2 multiplied rho is the air density. The A is the sweeping area of the rotor, which is basically the radius of the blade, and generate that area, the area size. And then the V is the wind speed in the cubic function, okay? But this give people, the C sub P is the power coefficient. This equation give people the wrong impression the power is simply a cubic function of wind speed. In reality, it's really not, right? If you look at the yellow line here, there may be a kind of cubic function somewhere along this part, okay? And once the control mechanism kicks in, and this curve is kind of bent down, change from the convexity to concavity, and then eventually kind of saturated here. And even this thin line in the middle can be described by some kind of function form. And if you look at the actual noise here, the actual measurement here, they have a lot of noise. If you do another function to the lower envelope of the wind data here, or do an upper envelope curve on the higher side here, if the middle part is a cubic function, obviously the two other sides of the envelope curve is not the cubic function anymore. Okay, the complexity in this equation is really coming from the C of P. It's not really a constant. As a matter of fact, the C of P, the power coefficient, is also a function of V. Okay, it's also a function of rho, and it's also a function of the wind direction, and more precisely, it's a function of the attack angle. It's how the wind kind of impact on the wind blade. So because of this kind of complexity, there's very hard for you to assume a fixed function form for this wind speed and wind power relationship. Okay, and the binning method basically being very adaptive. That's why the international standard body recommend that, and that's why it's being used very widely. It's still dominating the use of the in the wind industry. From this equation, people actually notice the wind speed is not only a factor of matters in the power production. So the air density rho here is also important. So they said, how you possibly to kind of factor in the air density part. In the IEC standard, they do provide something called an air density correction. Okay, so from this point onward, let's kind of focus on the power response part, right? We kind of provided the general kind of framework. We know many things we do here, and has the direct relevance on the reliability part, and the formulation also has quite similarity between the performance evaluation and the reliability evaluation. But we have doing more work related to the power response part, and so let's kind of stay on that part for the remaining part of the talk. for the response, because of the understanding from this equation, the rho is one of the factors affecting the wind power production. The IEC does recommend the air density correction, and which is also a simple formula you can use. You can calculate with the current measured air density and over the ratio of the standard sea level dry air density, and then multiply the current wind speed. Okay, and now you have the V prime, and after the air density correction, you simply use the V prime and the power output to establish a new power curve, and then nothing else changes. Okay, and then later on we come to argue, this may not be necessarily the best process to do the air density correction, or may not necessarily be the most effective way to account for the effect of air density. Okay, and not only us noticed that, the wind industry by and large also noticed that aspect. There's a group called the Power Curve Working Group, and which is really a collaboration of more than 40 wind energy organizations. Most of them is from industry. Okay, there are few academic members in that working group, and I went to a couple of meetings in that working group as well. They recognize the importance of having a multi-dimensional power curve that can account for not only the wind speed, they can also account for other things. They probably should be account for like the air density effect, not necessarily through that correction formulation, right? The way they are doing that right now is very much kind of multi-dimensional binning method. Okay, now here in the slides we showed you a two-dimensional. They call the power deviation matrix. It's basically two-dimensional binning method. So they have two inputs. One of the input here is the wind speed. The other input here is the turbulence intensity. The turbulence intensity is the standard deviation of the wind speed during the period and divided by the average wind speed. So it's very much related to the coefficient of variance concept in statistics. So they by doing this two-dimensional binning, you can have each small bins collecting enough data. You can compare, whether or not your new estimate of the power production, kind of consistent with the IEC method or not, right? The different kind of color here to indicate whether or not they are consistent or they are not consistent. The blue color here is basically said, the new estimate is very much in line with the IEC estimate. The red one is very much underestimate. The green one is kind of overestimate. So you do see there's a large area by doing the two-dimensional binning and by considering another factor, the estimate from the new method or the new factor is different from the IEC method, only consider wind speed. Now, the problem with the multi-dimensional binning is really the lack of scalability. You can easily imagine the difficulty runs when we have more variables, right? If you have one single variable like wind speed, suppose we have 20 bins here, and 1 year data, and in the wind industry, they usually arrange the data in a 10 minutes interval. So 1 year, you have about 50,000 data points. If you have 20 bins, if you divided this 50,000 data point in 20 bins, you will have 2,500 data points per bin. That's a lot of data. You can do many different things. You fit the distribution, that's no problem. Okay, but when you have two dimensions, suppose each of them still have 20 bins, and now you're going to have 400 bins. If you divided the 50,000 data point to 400 bins, you're going to have 125 data points on average. That's a lot of fewer than the 2,500 data points you had initially, but it still is probably many enough for you to do different things as you wish. Yet, if you keep going that kind of argument, if you add the third bins and fourth bins, right? If you have the three variables, each has 20 bins, you're going to have 8,000 data points. And then you don't have many data points left in each bin, so you have roughly about 8 data points. If you have 5 variables, each has 20 bins, you can have sufficient data point, you actually have every 60 bins to share one single data point. So this is really easy for us to understand. This is really kind of the fundamental issue of the curse of dimensionality, right? So the binning method basically just kind of fix that curse. So what do we do in this kind of to address this kind of challenge? About 4 years ago, we started working on this multi-dimensional non-parametric power curve model. Okay, and eventually the paper published in JASA application.
Hey, Professor Yuding, it seems like it breaks off a little bit.
Okay, so let me, I think my VPN is giving me a trouble here. Let me see if I can. Can you hear me all right?
Yes, it's good now. Are you speaking now, or it seems like I cannot hear anything now. Professor Yuding, are you speaking now? So it seems like Professor Yuding is experiencing some internet connection issues. But I think this might be a good time to collect the questions. If you have questions, you can go to the second tab here below and type in your questions, and I will pass that to Professor Yuding so he can take a look at them and try to address those questions. Raed, do you have any comments or questions? You raise your hand, so.
Can you hear me?
Yes, I can hear you.
Okay, I was wondering whether the data for the power curves is available online. Is it free data? And if yes, where can we get it from?
That's a very good question. Let's see. Can you type in this question in the Q&A tab so he can also see, because I think he may be disconnected from the internet now.
Okay, I'll do
so
that.
In the second tab below,
yeah, I see
the Q&A. If you can type it in, he will be able to see that.
Yep, perfect.
Yeah,
Thank
you.
Hello?
Oh, Professor Yuding, are you back?
Yeah, so I don't know what happened.
All right. Since we get this mini break, there are several questions. Would you like to take a look?
Yes.
So
let me give me a second. I need to get the. Do I still share my screen?
Yes, you can still see your screen. Are you sharing the ICE Binning slide?
Yeah. So you see that one?
Yes, I can see it now.
Okay, good. Okay.
So if you go to the Q&A question tab, I don't know if you can see that. There are two questions. The first question is asked by Ranjing. The second question asked by Raed Kanta.
Okay, so I only can see one question. Is the power curve available? And when can we get it from? Where can we get it from?
Yes, that's the question from Raed.
Right. So this question is answered here, right? The power curve generally is provided by the wind turbine manufacturer. So what they do, the power curve, is really kind of take the data. The data, this is measured on the side when they do the service or they do the testing. So they have the wind speed data, the power data, and then they feed this power curve. So the power curve is very much a kind of data-driven concept. And the way they feed the data is the binning method. Does that answer the question?
So I think.
Okay, the second question, do you just use a two-factor example to show that when more than one factor is taken into consideration, the binning method will be in trouble? Yes. So I use the two-factor example that if you only have two factors, you are not necessarily in trouble yet, because if you have like 50,000 data points a year, you have two factors, each with 20 bins, you still have a sufficient number of data points in each bins for you to either estimate average or estimate a constant parameter distribution. But typically, we don't really have only two factors. You can easily go to 5 factors or 10 factors in a commercial setting. And even with 5 factors, if each factor has 20 bins, you're going to end up with 3 million bins. You only have 50,000 data points. And then in the end, every 60 bins will share a single data point. You couldn't really do the very meaningful estimation anymore. Is the data available online? Okay, another question. No, the most of the time the data, the wind data are more kind of available. The power data you have to get directly from the owner of that wind farm. So one of the things I didn't mention here, but we are mentioned, I mentioned back in Beijing, I'm writing a book, and the title is Wind Energy, Data Science for Wind Energy. And hopefully that book can be published next year. And when doing that book, we actually try to collect all the data used in the research leading to that book, and then release that data to the general research community. So when that happens, hopefully that happens sometime next year, and then the data will be available. Now, there are some data set. For example, the data set we published the paper with JASA. That set of data set is available on my personal research website. If you go to the Texas A&M website, and then there's another link to, it's not on that particular website, but there's a link to our research website, and then you can find the data over there.
Thank you. One question you probably didn't see from your screen is a question from Ranjin. He asked, how does one consider the spatial temporal correlation of both input and output variables in the model?
That is not to be considered in this particular talk. You know, there's so we discuss a much broader set of issues in the book. So the first part is the wind speed, the wind field. The wind field has really rich spatial temporal part. So we did do some of the research along that line. And then the second part is more kind of on the single wind turbine performance, which is what we try to discuss in this talk. Okay, and for that one, you know, we kind of isolate a single wind turbine to say, if you're given this kind of input, and now how you're going to consider output. There's also a little bit kind of interactions between this turbine and the neighboring turbine, and sometimes we call that is a wake effect. But you know, there's a special techniques to handle that. You know, we do have a paper about the wake effect, and which is consider the special aspect in a more kind of specialized way. And the paper published in the IRE transaction early this year. Okay, and I see there's another question here.
I think he figured out the answer himself. So I think we have answered all the questions.
Okay.
Maybe we can go back to the presentation.
Okay, thank you. I think I'm kind of running behind. I try to kind of speed up a little bit. Maybe give a more kind of broader overview instead of all the technical detail. Okay, so please excuse me for this moment. I'm going to kind of write on the very fast trend and toward the end of the talk. So here we use this kind of kernel regression to handle this kind of multiple dimensional non-parametric power curve, right? Now, assume many of our members are familiar with the kernel regression, so I will skip this part. And this is really kind of standard figure taken from Hasty, Tipirani, Friedman's Element of Statistical Learning textbook. So, and I want to mention the IEC's method actually can be considered as a special kernel method by using a uniform kernel. So the binning method is basically like this, right? You have this kind of window. If you are within the bin, you are giving a weight of 1. You're outside the bin, you give weight of 0, right? The most of the kernel method we use, we don't really always use this kind of uniform bin. Actually, oftentimes we don't use uniform kernel function. We use a kind of smooth the kernel function. And like this is a Gaussian kernel function, right? And then they give different kind of data point, different kind of this smoothly decayed weight away from the center point, okay? If you only have one single input, whether or not you use the uniform kernel function, you use this kind of smooth Gaussian kernel function, it does produce some difference, but it's not a whole lot, okay? And the kernel function, the smooth kernel function, obviously will give you slightly better result. That's why people like to use this kind of smooth kernel function. But like I said, the result is not very striking. The real difference happens if you have to incorporate multiple variables. If the uniform kernel function will run into a curse of dimensionality problem, the smooth kernel function will too. So you have to accommodate the multiple input variable by devising some kind of model structure. Okay, and here when we defining or designing this kind of model structure, we make use some of the physical understanding behind us, and still we'll go back to that physical law of the power production coming from those kind of factors. So we notice there's a number of things we should pay attention with designing this kind of new model structure. There's a multiple important factors, at least 3 of them. There could be more. There's a functional relationship which is nonlinear, but we don't know because the C of P has other factors confounding with each other. And there's an interaction exists because if you only use manufactured models, you are not being very effective. Okay, so in the end, we come up with this kind of hybrid additive multiplicative kernel structure. And it's a multiplicative because each kernel element, we include 3 elements to capture 3-factor interaction. And now here, based on the physical understanding, we always have the first element as a V, second as a D is a wind direction, this is wind speed, and then the third one is changing with different kind of environmental factor. And now we have an additive structure, therefore the whole model is scalable. So you have 3 factors, you only have 1 kernel function here. If you have 4 variables, and then the 4th variable is going to be added to the second element. And then if you have 5 variables, the 5th variable is going to be added in the 3rd kernel elements. And therefore, it kind of allow us to capture up to 3-factor interaction and also give us this scalability of the final model. And what kind of impact it can make? And the impact is if you compare this with the IEC on multiple turbines, and you find that the error reduction over the IEC is really very striking. This is really not happen, not really kind of caused by randomness in data, right? It's over 20 to 45%. And this set of data we used in this paper actually is available on my website. If you couldn't find that, send me an email. I will send you the link. And this website, this data is free to the public. You can use it for whatever purpose you like to. Okay, and we also compared with a number of other machine learning methods because the IEC method is very simple and it's non-parametric, but it's kind of doesn't really kind of take advantage of the most recent the machine learning methodology development. So here we purposely selected a few representatives represent each branch of that method, right? The KNA is a neighborhood method, the SS ANOVA is a spline method, and the BART is a tree method. Okay, by comparing with this method, you can also see the AMK actually, number one, is pretty robust, and sometimes they do come to be very close to another machine learning method, but they can, they maintain pretty consistent performance. In one of the cases, they actually beat the best alternative, again by 15%. Okay, so the question is, you have a better, we have a better, more capable data science method, which can give us a better fitting of this power curve, and also account for multiple environmental variables. And what are we going to use that for, right? And we can use that for predicting for sure, right? So that is pretty easy to understand, and I'm not going to get into that prediction aspect here. I want to go back to that reliability question we raised before. If you recall, we hypothesize the efficiency curve, this bathtub curve for wind turbines, is not really like the typical machinery, which has a very long steady operation period. It actually has a noticeable faster decline after probably the initial 4 or 5 years. Okay, there's some initial evidence, data analysis to support this claim. If this is true, and people said, I'm not really ready to replace the wind turbine after 5 years, and it's a very cost proposition for you to do that, because install a wind turbine is costly, and upgrade that wind turbine probably is even more expensive. So what can people do these things? And there's certain kind of technology innovation to do something to retrofit a turbine generator. And this is known as a turbine upgrade. And hopefully by that retrofit, you can lift this kind of curve up a little bit, and even substantially. Therefore, you can have a longer, this stable operating condition, just like the other turbine machinery. And it turns out to be AMK actually plays a central role in quantify the benefit of this wind turbine retrofit or the upgrade. Okay, one popular upgrade option is install this vertex generator on the turbine blade. This is one of the vertex generator. You have to install a bunch of this. This generator on the slides, it's hard for you to tell how large it is. It's about a palm size. It's about your hand, right? The size. So you need to have an array of this kind of vertex generator on the turbine blade. And the theory says, if you get that design right, place it right, and you can increase the wind power production of aging wind turbine. Okay, and install this one, and in and by itself is not necessarily difficult, because they usually have a kind of glue underneath this surface, and then you can put that when you peel off that protection film surface, and now you simply just put the vertex generator on the blade. This is one of the reasons the vertex generator design and manufacture Smart Blade. This is a small company in Germany, kind of team up with 3M. So they are specialized in that kind of glue technology, right? They have very strong glue, and even you put on the turbine blade in the open air environment, it's not easily for them to kind of peel off after a certain period of time. Okay, but install this VT is not really free, right? And generally speaking, the cost of between $7,000 to $10,000 per turbine. If you have 200 turbines at a farm, and this is going to cost you about $2 million total. The question is how fast you can pay it back, right? How fast you can get those kind of investments coming back. That really depends on how much extra wind energy you're going to generate, okay? And from that process. And here I take one of the advertisement between 3M and the EDF is one of the major French-based wind energy company. They have a big presence in the United States as well. They said if you do this kind of vertex generator, you have an increase of AEP 1.5 to 3%. And therefore you can get your money back between 1 and 2 years. And this particular vertex generator, it is designed by the Smart Blade. So is that really true, right? If you have 1.5 to 3% improvement, as EDF advertised, does that really bring you back your money in 1 to 2 years? We did a simple calculation. If you do have 3% actual in the AEP, And if we consider 200 wind turbine in the 2 megawatts class wind turbine wind farm, and with the electricity sold at 6 cents per kilowatts wholesale price, and that 3% improvement in AEP can be equal to $1.2 million in revenue increase. Okay, so if you spend $2 million up front, you get $1.2 million actually every year, and 2 years, of course, you get the money back, right? If it's 1.35%, it probably takes a little bit longer time to get the money back, but it's not a whole lot longer. Okay, so that claim is actually true. The key question is that 1.5% to 3% is something you can expect. And this is the part actually is very difficult to decide. It is in the range of the general consensus what VG can do, right? The general consensus is really kind of between 1% and 5%. And here they said 1.3 to 3% is in that range. But detecting this kind of small improvement in a very noisy environment is not very easy, right? If you kind of remember all the data we see up to this point, all this kind of data you see here, the noise is much more than 3%. Okay, how you can detect this kind of small change and certify this is the correct detection, and it's not really kind of the noise, and that's become one of the main challenge. Okay, and I think I kind of run out of time, so let me skip. I stop at this problem here. Let me skip the next number of slides, which kind of get a little bit kind of into the detail part. And I can share the slides. I don't know what is the best way to share the slides, but if you need have a whole slides, I can send me an email. I can send you the slides. Let me go to the part we said why the AMK helps, right? The key issue is really kind of control the environmental condition, because when you have compared directly the difference between the power production before and after upgrade. Even you see a difference, that could be because the wind blows harder or weaker, okay? And here what we do is we use the model AMK to capture the old turbine operation characteristic, okay? This is the AMK here. By using this model to feed the AMK, almost it's a mathematical surrogate of the old turbine. It's almost like you take a picture of the old turbine and kind of capture how they operate. And then you feed the X new to the model. This is like running the old turbine under the new condition. And then you compare this predicted output with your observed output. If there's a difference, and obviously it's more kind of believable the difference is coming from the part you made the change to the turbine, okay? Now this is the general story. Actually, when we kind of dive deeper to solve the problem, it is not so easy. There's other kind of complexity involved. And one of the complexity is related to the bias part, okay? And because it's different, but sometimes you have this kind of bias over there, and the bias also can run from 2 to 5%. And here is one of the slides, and if you ignore this part, because it's a different kind of method, they basically said if we do the simulation study with the actual improvement we know, and sometimes they do have like almost like 2% difference. Yet the one you want to detect is about 2%. So with that 2% difference bias, and it's not very easy for you to pinpoint exactly how much effect you're going to have. Even sometimes you're going to be very hesitant to say it is positive effect or negative effect if your effect start with a small number, for example, 1%. But if you have 2% negative bias, you could end up with negative 1%. Okay, so we did something to address that issue, and in the end, we have a kind of version of a kernel method. We call it the AMK, the kernel plus. It's really AMK with that bias correction, and we are not able to entirely eliminate the bias altogether, but we were doing much better than the existing method. Okay, but this is only demonstrated on the simulated result. And for the real power production, because you couldn't run the experiment, so it's very hard for you to see, compare with the actual, you don't really know the actual upgrade effect. So people said, how can you sort of validate? And we did a blind study with one of the major power company. And they provided us 3 wind turbines with the data, but they didn't really tell us how many turbines they had added this upgrade, and whether or not there's any turbine being upgraded. Okay, and they only said there's 3 turbines, and analyze the data, tell us what you see. Okay, so there's 4 possibilities: 0 turbine being upgraded, there's 1 upgraded, there's 2 turbine upgraded, they all 3 upgraded. So we did all the analysis, and eventually we tell them the 3rd turbine is being upgraded. Okay, and they kind of confirmed our detection is correct, because they want to do the blind study without telling us the underlying truth up front. They're afraid of we overfit the data just to try to kind of confirm the result. So here, the blind study lent certain kind of degree of credibility to our method. We also did the joint study with this small company, Smart Blade, because once they heard about our analysis and the method, and they have their own internal method, they want to do a kind of study with ourselves. And the study kind of showed a high degree of consistency between their method and our method. And when we do this kind of study, also, they only give us the data, they ask us to do the analysis without telling us what the result they have in the first place. We did a 2 wind farm case study. One is a little bit kind of medium complexity terrain. Another is very flat terrain analysis. So in both of the cases, we see a high degree of consistency between their industry method and our method. Okay, and so last year, upon knowing the joint study we did with the Smart Blade, the EDPR, which is the number 4th largest wind owner operator, and they had a long relationship with us, and eventually decided to sponsor a year-long fine-tuning of this kernel plus method, and did extensive case studies with them, use their own data. The data come from 3 different kind of wind farm, 3 different kind of turbine types, and 10 pairs of turbines, and we used. So we were able to, and the postdoc did the study is Hong Wang Pu, and so he built our package for the EDPR. I believe the EDPR is constantly using that. Okay, and this kind of conclude the talk, and I really want to acknowledge the former and current student contribute to this research, and all the financial support and the data sharing, and our industry partner and the federal government to provided us. The last 2 slides is really the references and all the papers where you can find them, and just in case you want to get further detail of the references. So I like to stop here, and if you have further questions, I like to entertain them. And apologize for the fast rushing through for the later part of the slides.
Oh, thanks, Professor Yu Ding, for this amazing talk. So if you have any questions, you can raise your hand. There's a button saying raise hand, and I can unmute you, and you can talk. I think the main question, Professor Yu Ding, is how can the audience get this amazing slides you presented?
Actually, I don't really know. You know, I think this question probably. Can you send the slides to the QSR email listserv? Is that something?
I think we can upload it to the QSR website, because this webinar itself has been recorded, and the video will be available to all QSR members.
Right. So I'm a little concerned about the recording, because there's a disruption in between, right? I don't really know how that goes.
I think it seems to be fine, because it's recording on the cloud, so it will just record the break. And
okay. So I can send the slides. Number one, whoever like to have the full slides can send me an email. I can send the slides directly back to them and point out to where you can find the data already released. And we're going to release a much more data sets upon the publication of the book next year. I can send the slides to Lincoln. So Lincoln, you can feel free to do, all the information are public information. So you can do freely to do whatever you see fit.
I think that would be great. That would be great.
Mm.
So that's about the slides.
Okay.
Any other questions? Well, so I guess probably most of the questions were asked during the break, the middle break. Mm-hmm. I think the presentation itself is really clear. So if there's no more questions, let's all thank Professor Yu Ding. And if you have any questions about about how to have access to the slides or the video, please don't hesitate to email me. We will make this video available to all the QSR members.
Well, thank you very much for coming to the webinar.
All right. Well, Professor Yu Ding, thanks for giving this presentation and the support
thank you.
of the community.
Okay.
All right. We should stop recording.